Hi everyone, it's a great honor to make a contribution to this amazing workshop, especially that it's exactly the faculty from which I graduated almost exactly 1 year ago, so it's doubly exciting. And today I'll talk about a joint work that already Sebastian hinted about. It's among others with Sebastian and Nicolo, who's also in the audience. We propose a graph-based method to detect in an automated way laser cooling schemes for ultracold molecules. So probably in this audience, I don't need to explain that producing ultracold molecules is a challenge. They give lots of promises, but so far, we would love to have more species that are ultracold. One of the very useful approaches are, of course, all kinds of indirect cooling. However, I think we all can also agree that the species that we obtain that way are maybe not the most typical chemically. So if we would like to have something more chemically typical, maybe something that is much more useful for astrochemistry or ultracold chemistry, laser cooling would be a natural shot. The problem is that so far we, as a community, believe that this method is really limited to molecules that have diagonal Franck-Condon factors, and as a result, we also produce pretty atypical chemically molecules. And as already Sebastian hinted, his group actually found already laser cooling schemes for carbon dimer and actually also for OH+. And both of those species have strongly orthogonal Franck-Condon factors, which basically begs the question, how many more molecules are actually laser cooled if we remove our let's say biases. And as Nicolo can vouch for, search by hand is really painful for such laser cooling schemes, especially when you even abandon this guiding light of diagonal Franck-Condons. So what we propose is to let's basically ask a machine to do it for us. And to do it, it requires a very simple switch of the representation. So if you think of a molecule and its electronic structure as a graph, then you can use very efficient, highly parallelizable graph-based approaches, graph-based searches, to localize a subgraph that represents a laser cooling scheme. To do that, actually, what you need to think, how you need to think of it, is you take every energy level that you are aware of, you represent each energy level as a node of a graph, and then you track every possible decay channel between those energy levels and represent them as a connection between those nodes. As a result, you get one huge graph representing a molecule, and then what you need to do, you need to locate a subgraph that meets a set of conditions, making it a viable laser cooling scheme. So all that is left to do is to determine the set of conditions that this laser cooling scheme has to meet. And here comes my amazing collaborators that know exactly what a molecule has to do in order to be laser cooled. So what we do, what are those steps to detect laser cooling scheme? So first thing is to detect states, energy levels that can be your starting states. So this means that this energy levels needs to be populated by molecules having some initial temperature that you prepared your gas. It has some initial temperature. Therefore, you have some energy levels that are immediately occupied. So they are usually lowest energy states. So this is one condition. Second condition is the lifetimes of those states has to be long enough so you have time to pump it up to the excited state. So next is you need to identify all possible states that decay to this to this to the starting state. This we call reachable excited state. This will be a basis for your laser cooling scheme. This will be the one that you keep that keeps spontaneous decay, and then you pump it back. The only condition it has to meet is that there exists a decay channel between them. So because that means that then you can pump it back, but also that the energy difference between those two energy levels has to be addressable by the lasers that you have in your lab. So you have to just put a condition on the distance between those energy levels. And final step for this graph-based search is you need to identify all states to which this excited state decays to. And again, if you want to pump it back successfully, the energy difference has to be within the right range of your lasers. So there are a few details there that I'm happy to discuss later, but I think the main message should be clear. Importantly, when you use this algorithm, you tell how many lasers you want to use, meaning how many transitions you want to address maximally, and it gives you it returns to you all laser cooling schemes ordered by closure and by the cooling time. And importantly, by what we mean as viable laser cooling scheme, it's closed enough that you can cool it within cooling time. So that's the main condition that is being computed for each of those subgraphs. And now using the power of parallelization, instead of doing it really one by one, you identify all starting states in parallel, and then for each of those starting states, you do the procedure in a fully parallel way, meaning that this algorithm is pretty efficient. In a moment, I will tell you how efficient and how fast. But basically, Python would struggle a lot if you would like to do it hand by hand. And if you do it using specialized graph library, graph database, this is a breeze. So I told you just about the method. Now I will flash some results. And again, it will be really just flashed. But we made a scan through several molecules that we found interesting in an ExoMol database. And as a natural playground, we first chose carbon dimer because my collaborators worked on it before, and not only recovered all laser cooling schemes that Nicola found, but we also found some new ones. And in particular, it's interesting because they are in the higher rotational branches. So if you want to get ultracold molecule at non-zero rotational angular momentum number, this would be a molecule you could look at. We recovered a new cooling scheme for CN. For YO, even though we know it's laser cooled and is very efficiently laser cooled, we detected more than 1,000 laser cooling schemes. And also interestingly, we look at CO2 with our drive to look for more chemically typical molecules. And there is a laser cooling scheme that is viable by our definition, but not by maybe definition of modern setups, because it takes 6 minutes to cool down. However, it is doable in theory. So, but this shows you the power of the method. This didn't take long, and we already produced multiple new laser cooling schemes. We have also some negative results. My saddest negative result is we were hoping so much for ultra-cold water, but at least it doesn't seem like it's the case. Okay, so our aim is to make this method widely accessible. So we're working hard on tutorials that will explain first simplified version of the algorithm and then the full-blown version of the algorithm. I hope at some point, I hope it will be fully understandable. Nicola will be my test case. And regarding the scaling and efficiency that I was praising. So on one hand, it's really fast. So on the right, you have on the left, you have diatomic molecules, that have up to 100, 100,000 of states and 10 millions of decay channels. The whole search and whole loading of data preprocessing together, it takes 6 minutes. So it's pretty nice boost. However, when you go to truly complex polyatomic molecules, well, it grows to 2 weeks. And when it comes to scaling, why it's so difficult, it's actually not the number of states, it's a number of decay channels that messes out the computations. And you can see it here. So those are the largest molecules we tried to tackle. CO2 is 1 hour, which is, I think, still fine. With water, you increase number of decay channels by 2, and your preprocessing and search increases from half an hour to 2 weeks. So this is terrible. And then NH3 that has 17 billion of decay channels instead of 6 billions is basically out of scope for the current implementation. So that's the first outlook that we have. So I see the way to make it more efficient and make it better, but it's still ongoing work. But the other outlook is much more the limitation is much more fundamental. So to look for all those subgraphs, we need to have a simple way of estimating cooling time. In theory, there is nothing that would stop us from looking for very complex cooling schemes like this, like multi-level ones. But we don't know an easy way to estimate cooling time. So far we limited ourselves to those kind of simple cooling schemes. So also a disclaimer, up to this negative results are only about this simple laser cooling scheme. So maybe if we go more crazy, something new will appear. Yes, so that's it. So the take-home message is, if you change the representation of a molecule to a graph, you can take advantage of super parallelizable and efficient graph-based methods to search for a viable laser cooling scheme as subgraphs within this large graph. Disclaimer, we can only be as good as the data that we have, and in particular, we use XML database. And of course, I want to thank a lot my collaborators, Nicola, Sebastian, and Daniel, who's not here, and hopefully archive is on the way. Thank you so much.
Okay. Thank you, Anna. Right, we have time for some questions.
I would have a question, and maybe you can answer and help me out of my puzzling situation a little bit. So I know graph space as a certain type of entangled states, which can be well prepared, well described, well measured, and it's a clear recipe to doing, for example, quantum error correction, all these things. So now, are you saying that all molecules can be described as such graph states? First question. Mm-hmm. Second question is, how does it relate to laser cooling of the molecules? Mm-hmm. Because in laser cooling, you have no entanglement. I mean, you change phase space density, you have dissipation and all these things which contradict entanglement. So what exactly do you mean by graph?
Yes, thank you. So I'm really sorry for confusing you. I mean, I never meant any graph state. I meant graph as nodes and connection between nodes. So it's basically a form of data. So you can have a table, you can have a graph. So yes, sure. So the energy levels, when we think about electronic structure and we look at energy levels, there is an ordering that will disappear, you're right, when we represent it as nodes. Though now the nodes are completely chaotic. They are randomly ordered in this representation. But what provides an interesting change of perspective, so now you can, when you are in some excited state, you can decay to some lower lying states, right? So those will provide connections, links between nodes in your large graph. So in other words, this graph will have paths that describe the decay between a node to a node, so a energy level to an energy level. Yes. Yeah, no entanglement, no state. Yes, I'm very sorry. So that wasn't my point to confuse. So it's really just a change of the form of the data. Instead of a table, let's do a graph.
Hi, very nice. I have a question about the scalability that you just mentioned. I assume this is when you're trying to search for like the full graph, right? But if you just want to find one reasonable scheme,
yes. Sorry. Yes, this is a bit under the hood. Those numbers are for the whole graph. What really matters is this moment. Hold on. Maybe actually even this moment. So this red dots are the starting states. Usually they are of order of 100, maybe 500. And then you follow, then you find those excited states. Now your graph increased, the size of the graph increased, and then all possible states that they decrease to. So actually what really matters is, it's a good point, is the size of this graph, because this is where you're gonna search for a viable laser cooling scheme. It just happens that usually it's proportional to the size of the whole graph. So here, not to make it too complicated, I printed those numbers.
Okay, but you mean that even for that limited graph, like you can still not do ammonia?
Yes, because the other thing is, ammonia has extremely dense graph there. Number of connections is just so crazy, and it's already here at this level. I think we have 1 million of states. So even if we went down from 5 million to 1 million, it's still bad.
Yeah, too bad.
Yeah.
Nice.
Yeah, I know. No, but we'll do it. Ultracold ammonia is the aim.
Thank you very much. I'm interested about how much information are you putting in each node and edge, in the sense, I mean, each node is a state, so the label and an energy, but I guess there's much more.
Yes.
Also in the edges, like transition probabilities or much more.
That's
May you summarize a bit? I'm really interested.
Yes. So to limit the let's say the weight of the graph, we really need to use just the crucial information. The crucial information will be the one that is needed to compute cooling times and all that. So in particular, in the edges, we have branching ratio, which is basically like transition probability just divided by all possible exit channels from via level. So that's the only thing. Okay, plus the difference of the energies. So those are two properties sitting in the link. And in the node, there is energy and the lifetime. But of course, then you always have the index of the state. So if you go back to the graph database that you have, you can always go and look for all quantum numbers there and all state specification that you need. Just to limit the load for the algorithm, we keep it as simple as possible at the graph database level.
Okay, one final very quick question.
Hi. Maybe it's on this slide, but
yeah, it's okay. I hear you.
I was wondering about how you calculate the cooling times. Like, does it have to do with like the scattering rate, and then are you assuming some like initial temperature for the molecule, and then like does it depend on the wavelength of the laser you're using?
Yes, exactly. So we make a very crude approximation, or maybe I don't know how much. I think it's crude approximation. Where we assume the initial momentum of a gas, right, depending on the initial temperature. Then we compute mean photon momentum that we use. That depends on the this doesn't work, but it depends on the transition wavelength and the branching ratio. So this is the mean photon momentum, and then to compute how many events you need, you divide one by the other, and then you divide by this scattering rate. So it's coming from those two publications. We are very happy to use equations from.
What initial temperature are you using for the gas?
So we do. It's again crude approximation. I told you I put this in here. we have this condition for the starting state, that it has to be some energy below some energy, and then we transfer this energy to kelvins, and this is the temperature of the initial gas. So what's interesting here, we can, for example, assume 500 Kelvin gas, which is pretty hot, and this will allow us to access some higher lying states as a starting states. But it may happen that then you find some very nice cooling scheme that will still, that will make up for this heating. So, but again, good approximation.
Okay, let's thank Anna and all of the speakers from this afternoon again.